Minasan, konnichiwa. Zamurai Engineer desu. In this video, let us continue with our differentiation. We will do the differentiation by means of numerical methods. And in this topic, chapter 2, topic number 2, we're going to discuss about backward difference approximation method. So we know, again, the same definition in calculus that the first derivative is the limit of the function fx plus delta x minus fx over delta x as delta x approaches 0. And for a finite delta x, we have the approximation fx plus delta x is minus fx over delta x. As we already talked about and explained lengthily on our previous module. So in this module, if delta x is chosen as a negative number meaning we are going backward. That's why this method is backward difference. Okay, as contrast to our preceding module, which is forward difference. So we'll use delta x here as negative. So as you can see, our first derivative is now equal to fx minus delta x minus fx over negative delta x. Okay, please take note of that. And because that is the first derivative, we can what? We can simplify the rational number into fx minus delta x over delta x. Okay, the position of fx and fx delta x changes, no? Because now delta x is negative. Okay, remember that. This is a backward difference approximation as you are taking delta x backward from x. So we are having the value of x, delta x that is positive going there, delta x that is negative going backward. Okay, to find the value of first derivative at x is equal to xi, we may choose another point delta x behind. This is equal to x is equal to xi minus 1. This gives the following equation. This is the equation that we need to evaluate. We need to recall. We need to remember, and we need to implement. Okay. Okay. Take note. Delta x now is equal to xi minus xi minus 1. Okay. And as you can see on our typical diagram for these things, x is our target point where we need information of, for example, what is the value, what is the range. We need that to calculate, we need that to evaluate, to compute. Now, you'll notice that we need another point in order to find out the slope. We cannot solve the slope with only one point if we are talking of numerical methods. You can do it in calculus with only one point. That is calculus. Okay. Now, since we are doing numerical methods, we need another point, and therefore, instead of going ahead of x, we are going back from x. Going back from x and going to 0. So going backward, no? So that is x minus delta x. So this is graphical representation of backward difference approximation of first derivative. Example 2. The velocity of a rocket is given by, so the same example, but now our our questions are different because letter A question is now use of backward difference method for the first derivative of velocity function of t to calculate the acceleration at t is equal to 16. We want the acceleration at time 16 seconds. Use a step size of delta t is equal to 2 seconds. The same value for delta t. And letter B, find the absolute relative true error for part A. Okay, so the same problem, but now using the backward difference method. Okay. Now let us solve this problem. Solution. Okay, we can lay down all the given data. T is equal to 16, delta t is 2, and therefore our t plus delta t or t minus delta t is actually 16 minus 2 is equal to 14 seconds. And therefore, we are interested in what? Acceleration at time 16 is equal to velocity at time 16 minus velocity at time 14 divided by 2. So therefore, there are two things that we need to evaluate. That is what? Velocity at 16 and velocity at 14. So let's do it. Velocity at 16, use the same equation, but replace the variable t with the value of 16. And you can find out using your calculator, practice at home, use your own calculator. You will find out that the value would be 392.07 meter per second. Okay. This is the same thing on the previous module. Okay. We already solved this velocity at 16. Now, what about velocity at 14? Just replace the variable t by value of 14. So just replace, and you will find out that the result would be 334.24 meter per second. Now, we have the two values necessary in order to evaluate acceleration. And then just what? Substitute the value for velocity 16 and the value for velocity 14. We have what? 392.07 minus 334.24 divided by 2, and you will have the answer 28.915 meter per second squared. That is our answer for letter A. Now, let us continue in order for us to get an idea of how far we are from the true value. We can compute the requirement of question number letter B. What is the absolute relative error? So because we know the true value and we know the approximate value, therefore we can calculate absolute relative true error by using the absolute sign. 29.674, that is the true value, and our approximation is 28.915. So therefore, subtract this value from 29.674 and divide by 29.674, and you will get what? The value 2.5584 as our absolute relative true error. This is the error, and also less than 3%. That is accepted, no? Accepted. Not just less than 3%. It is less than 2.7, which is our answer on the forward. But don't be misled. Forward is not always having the greater error than the backward. It just so happened in this specific example. In other example, we can expect that sometimes forward difference approximation method may give us lesser error than the backward. It just so happens. So what you can do is calculate the forward and calculate the backward and compare and use the smaller error. So in this example, we can use the backward approximation method, backward difference approximation method, because it has given us the lesser amount of relative true error, okay, which is 2.6 versus 2.7. So it's very small matter. Very small matter. They are almost the same. But the important thing is less than 5% and even less than 3% error. So that is our discussion for this module about differentiation using backward difference approximation. If you have any question, please use our comment section below, and we'll try to get back on you on your questions. If there are none, again, this is your professor, Dr. EYPEI, preaching engineering for nation building.